let me add delays to these operators. For that, we'll create one more project. In that project, we'll add the delays and check whether the output is performing as intended. So let's start creating a new project. And to create a project on data flow, gate delay. It's an RTL project. I want to create Verilog file. VF gate delay. Next, select the board. Finish. Would you like to close this project? No. Let's we'll assign inputs there. Okay. Now let's start writing the project. So I am taking one output and two inputs A comma B. I have to define my output as out and inputs as input A comma B. In this example, what I want to show is I want to add the delay to the assign statement. So before adding the delay, we'll do without delay once and then we'll check the output, then we'll add the delay. My output is equals to A and B. Okay. I'm saving it, and first thing is you need to check the schematic. The schematic is correct. Now we'll run the simulation, behavioral simulation, without any test bench, right? We know how to give the test vectors in the runtime itself. So we'll use the same method here also. Now you can see I have defined output as the first pin. That's why output came here, and input and output you can rearrange them if you want. By default, the inputs are in high impedance state and the output is in don't care condition. Now I want to apply force constant, binary value of 1, and let's say binary value of 0. Let's run it for 10 nanoseconds. Now you can see as soon as the input changes, the output is changed immediately without any delay. You can see at the edge of the transition also. See, there is no delay. As soon as the inputs are changing from their z value to corresponding 1 or 0, the output is also changing from x to 0 based on the operation that we have performed. Here we are performing AND operation, so 1 and 0 will be 0, right? If I run the same thing for, if I change the output, let's say to 1, and run the simulation for 10 nanoseconds, then we'll see whether it is changing or not. Yes, it is changing. See here, as soon as the B input is changing from 0 to 1, my output is also changing without any delay. Okay. So now let's add some delay to the assign statement. You can add delay like this, asterisk 10 nanosecond delay. I want to give a 10 nanosecond delay. Save it, and then we'll relaunch the simulation. Put window. There by default values. Now I will add A is equals to 1 and my B is equals to, let's say, 0. So what are we expecting? We are expecting a delay at the output node, right? So let's see whether it is happening or not. I'm running the simulation for 10 nanoseconds. Let's see. Even though A and B are changing, Even though A and B are 1 and 0, there is no output because we have given a delay of 10 nanoseconds. Until 10 nanoseconds has passed, it won't give any output. So I'm keeping the same value of 1 and 0 and running the simulation for 10 more nanoseconds. Now see, the output has started changing, right? You can see the output is changing and this output is evaluated at this particular node of inputs. Okay, what I mean is, if the inputs we have seen, the if the pulse width of the input is very small compared to the delay we have given, then it will get surplused. So we'll see what it is in the example. In this practical example, let's give my A, let's give my B to 1. Let's assign B to 1 and check and run the simulation. So now see, even though B is changing from 1, ideally the output here should be 1 into 1 should be 1, right? But still my output is giving 0 because until 10 nanoseconds, after 10 nanoseconds, then only the output is assigned to the actual output. See, at the edge of 10 nanoseconds, it is assigning. So I am running it for 10 more nanoseconds. Then you can see now the output is correct, right? And it is evaluating at this particular node. What I meant, I will show you. Let's give an input of 0 to A for only 5 nanoseconds. Okay. So my A becomes 0 for 5 nanoseconds. And then I will give my A again to 1. I'm converting my A again to 1. Let's say I will do the simulation for 10 nanoseconds. Now let's see what happens. There is no 1 into 0 is happening, right? Ideally, this 1 into 0 should appear after 10 nanoseconds, right? But the pulse width is smaller than the delay. It was surpassed. It is doing the operation of 1 into 1, right? It is not doing a operation of 1 into 0 because, as I said, the delay element will execute first and then the expression will get calculated. So what happening is, up to here the output is evaluating with these inputs, right? Then we expected this 1 into 0 should appear here, but still it was not appeared here because after 10 nanoseconds has passed, it will evaluate the expression A and B at these inputs, not these inputs, because these inputs are already forgotten by your circuit because it went into the delay and then it will evaluate the expression at this particular time period, right? This should be very clear because this will be very helpful to eliminate the glitches inside your circuit. The glitches are nothing but the short pulses that are appearing in inputs. So we can eliminate those glitches like this. I don't want to have this data, so I eliminated by giving larger delay to my expression compared to the pulse width of my input. This is very important topic while you are designing some real world applications. Okay, this should be clear because we have applied, even though we have applied 0 in the input pattern, there is nowhere you can run the simulation for any amount of time, but there is nowhere this 1 into 0 is getting evaluated, right? The output is always staying at 1. To get this evaluated, this pulse width should be greater than the delay. See, the pulse width is only 5 nanoseconds from 1040 to 1045. To get this, the pulse width should be greater than the delay. So I'm again writing it to 0 to show you how to get the pulse width greater than that. And I am running it for, let's say, 30 nanoseconds. Now the A pulse width is 30 nanoseconds. See, it started at 1075 and it ended at this 101105. Now see, the A is changing at 1075, but the output is not changing until it waits for 10 nanoseconds. 10 1085. At 1085, it is exactly changing to this output 1 into 0, right? Because it will evaluate at this node. At this node, still my A is 0. So my output is 1 into 0, which will be 0, right? This is very, very important topic and very tricky topic, which will be very useful. So now we have created a delay, and I want to see whether the delay is really synthesizable or not. As I already mentioned, this hash trick 10 will give you a 10 nanosecond delay, but it is not a synthesizable delay. What I meant is the FPGA board don't understand this thing, but it is giving output in simulation level. But if you implement this design, it won't give you this 10 nanoseconds delay, right? So to give you a practical example, I will try to synthesize this and then I will run on the jetboard and see whether it is really giving the 10 nanosecond delay or not. 10 nanosecond is very difficult to visualize, so I am giving a 1 second delay. So 100. So how many zeros? 3 zeros, 4, 5, 6, 7, 8, 9. So this is a 1 second delay. Let's give this delay, and first we will verify the simulation also whether it is really giving 1 second delay or not. See, the circuit hasn't changed. Even though if you have changed, if you added the delay element, circuit doesn't change. That means it will only evaluate the functionality of delay, but it will not add any extra circuit to it. So let's give the inputs: force constant, binary of 0, force constant, binary 1. And then since our delay is in seconds, we have to run the simulation for at least milliseconds to visualize it. Now my output is still 0 because after 30 nanoseconds it won't give me output. Let's run it for seconds. Now the output is 1. At what time period the output become 1? It become 1 at 100 milliseconds, right? This is not 1 second, this is 100 milliseconds because only 8 zeros. If you add one more 0, then it will become 1 second. So I'm saving to show you 1 second delay. I'm relaunching again. Now let's apply the test vectors. Force constant, both are ones. Let's see. A is equal to 1 and my B is also equals to 1. Okay. And I am running the simulation for, first I will run for only 900 milliseconds and see whether the output is changing or not. No change. Now I will run for 150 milliseconds more. Now see, exactly at 1 second, this is 1000 milliseconds, which is 1 second. Exactly at 1 second, my output is start changing and it is responding to the values of input, right? So now let's run this code and implement this code, and we'll see whether the 1 second delay is really happening inside the jetboard or not, whether it is really synthesizable or not. So let's do synthesis first. In this example, I don't want to copy the constraint file like we did earlier, right? Like we did when we did full adder case, we have copied the jetboard master XDC file and we have edited the file. But I want to show you how to write the constraint file using GUI. So for that, first I am running the synthesis. Before going to write the synthesis, I want to open my schematic. So this is my schematic. So the synthesis is running. You can see the synthesis is complete. It is asking to run the implementation. So let's run the implementation. So this is the output, right? I want to assign these inputs and outputs to some of the pins of my board. That is the purpose of the constraint file. If you don't give any constraint file, it will assign some random pins. So let's see what happens if you do without pins. So it is running the implementation steps like run of design. You can even see how much time it is taking. You can see if there is any errors or warnings in this message window. There are no errors right now. Once the implementation is done, we'll try to create the bitstream file. Before creating the bitstream file, let's open the synthesized design once and we'll see the synthesized netlist. So this is the synthesized design. This is our board. Now the implementation is also done. We want to see the implemented design. So you can see different kind of reports, power, what is the amount of power it is taking and all. So where is our design? We'll try to show the connections of the design. So this is where our design is sitting. See, these are the wires that are connected. Since we haven't given any constraints, it has assigned some random pins to it. So this is my, let's see which one is output. These two are my inputs, right? These two pads are my input pads and this is my output pad. You can see this is the output pad and these two are input pads, right? So this is where the design is implemented. I have one output and two inputs and they are connected to the CLBs like this. So the AND operation is implemented using only one slice inside the FPGA. We'll explain what are slices CLBs in the FPGA architecture. But right now consider it has used only one LED to perform the AND operation. It has taken two inputs and the output is connected to this output pin, right? Now you want to see the inputs and outputs in the board. For that, we have to assign the pin names to that. So how to do that? First of all, we have to see the board pin configuration. So I'm opening the board pin configuration. You just type the board pin out and open this link. You can see this is the image of the board. So the switch 0 has a pin name of F22 and switch 1 has a pin name of G22. So I want to assign switch 0 and switch 1 to my inputs A and B like this, and my output I want to see in this LED 0, which is T22. So let's do that. Let's assign these pin names to our design. So I'm opening our design. So how to do that? First of all, you open the schematic. You can write, you can edit this file whatever we did last time, like you can copy this board master file there and then you can edit the information, or you can create like this. You open the schematic and click on this IO ports, then you'll have this window. In this window you can assign the pin names. What is the pin name we want to choose? We want to choose SW0 and SW1, which are F22 and G22. So I'm assigning F22 and G22 pin names. For A, I'm assigning F22, and for B, I'm assigning G22, and for output, what is the pin name? I want to show in this LED, which is T22. Output is on T22. You can write T22. Okay, and by default it is at LMCMOS 1.8, but we want LMCMOS 3.3, so I'm selecting LVCMOS 3.3. LVCMOS 3.3. This is the standard of IO. What this says is the input output ports are operating at 3.3 volts, which is by default the JET board is having 3.3 volt IO ports, so I'm assigning it to 3.3. Now I just need to save this, then it will ask save the constraints. So I want to create a new constraint file. This is my XDC for gate delay, creating it. Okay, so now let's see, it has automatically added the constraint file in the sources, my XDC. So what we did, we have assigned A to pin F22 and B to G22 and out to T22. And we have defined LVCMOS 3.3 volt standard for these three IOs. Simple, right? Very simply we have created the constraint file. Now let's run again the synthesis implementation and generate bitstream. I am directly running the implementation, so it will do the synthesis as well. Once the implementation is done, we'll see whether it is really assigned to those pins that we have specified, right? Earlier it has assigned random pins. Now we'll see whether it has assigned to the pins that we have specified. So let's wait for the implementation to be done. So by that time, I want to connect my JetBoard to the laptop. I have connected the JetBoard. We can go here, open target, this program and debug section. There is a section called open hardware manager, and then click open target and click auto connect. Now it is trying to connect to our JetBoard. It has connected. You can see Xilinx Digilint. Okay, server XDP we don't want, so click OK. Now the implemented design we can open and check whether it has really assigned the pins to it or not. Now let's see where is the connection. Yeah, see, earlier the design is implemented somewhere in this corner. Now the design is shifted to near the pins that we have assigned, right? These two are input pins. The name is G22 and the other one is F22, right? F22. These two are inputs. You can see the input name as well, A, and this is the other input, B, right? You can see here B. These two are inputs, and my output is connected from all the way here. It is doing the operation in this LUT, and then it is connecting it to output somewhere here, right? This is my output, which is T22. Okay, see, the signal is transferring from this location to this location, which is very huge amount of wire. You can see the wire is very small here, but if you consider it in, the wire is in nanometers, so if you elongate it, it will be in kilometers as well. So this will create lot of delay. That's why the delay is very important thing whenever you design any circuit, right? The functionality will be same, but because of delay your circuit might fail. See, there is a huge amount of delay that it is associated with just this simple AND gate. Let's say my other AND gate is sitting here and it is very small delay. Then the output of this AND gate and this AND gate is connected to some other gate. So what happens? This AND gate will give me the output very quickly because it is having very small delay and it is very near to the next block. Then this output will take more time to come. So they are not coming at the same time period, that will cause the failure of your circuit. This is what we will do in static timing analysis, what we will check whether the inputs to a particular block is coming at the same time or not. By using static timing analysis, we'll explain all these topics in the advanced topics. So right now we have implemented. Let's dump the code. So before dumping the code, we have to generate the bit stream. Click on generate bit stream. Okay. Now it is showing we are running right bit stream. We have done the synthesis complete. Now it is trying to run the bit stream. Once the bit stream is complete, we will dump it into the JetBoard and see the output. So as I explained, this 1 second is not a synthesizable thing. So we'll see whether it is really giving 1 second delay or not once we implement in JetBoard. So running right bit stream, it's done. You can open the reports or you can open the hardware manager. Now you can start programming your device by using the bit file that we have generated. Now see, once the program is dumped, this blue light should on, then only it means the program is dumped inside the JetBoard. Okay. Now what I am doing is I am applying inputs 1 and 1. If both the inputs are 1, see the output is glowing. Immediately it is glowing, right? There is no 1 second of delay. If I am changing one of the input to 0, immediately it stopped. Again I am changing to 1, it start glowing. So there is no 1 second delay. But we have given delay in our Verilog code, right? This, but it is not synthesizable. We'll add the synthesizable delay by using a system clock that is available in JetBoard. The system clock that is available in JetBoard is a 100 MHz clock, which is very high frequency. So we'll use a clock divider circuit to reduce the high frequency clock to low frequency, and then we'll use the delay block to control our circuit. So we are going to see the delay blocks when I teach you that behavioral modeling, in where I will teach you some important blocks like initial block and always block. There we'll use the system clock and then we'll assign some synthesizable delays to our design. So let's move to the next example of 4:1 multiplexer. So I'm creating a project. 4:1 multiplexer in data flow modeling. Data flow 4:1 multiplexer. 4:1 mux. In this, I'm going to teach you two different ways that you can design a multiplexer. One way is by using logical operators, and the other way is by using conditional operator. So in this first example, I'm using logical operation LO, and I'm creating a file mux underscore LO. We'll select the JetBoard as usual. You want to close the project? Yes. So, so let's start writing the code. I'm going to design a 4:1 multiplexer. 4:1 mux. So what are the inputs and outputs that is required? One output and four inputs I0, I1, I2, I3, and will require two select lines S1 and S2. Same order I am defining. We will require an output I0, I1, I2, I3, and two inputs, control inputs S1 and S2. So I am declaring the ports here. Output, out, input I0, I1, I2, I3, I4, and no I4, only I3, and we'll have two control signals S1, S2. Yes, now there is no error. Now we'll use the assign statement, and then we'll assign the output using the logical operations like this. So what does the 4:1 multiplexer is made up of? It is made up of four 3 input AND gates and a 4 input OR gate, right? We'll require, what do we require? 4, we require 4 3 input AND gates and 1 4 input OR gate. In gate level modeling, we have seen how to implement this using logic gates, right? But right now I'm doing using logic equation. Just follow the equation. What is the equation? First of all, we want S1 bar and S0 bar. See, this is an unary operator which will do the negation of this variable S1. So S1 bar, S0 bar and I0, right? This is the first 3 input AND gate. And then we'll do the OR operation using logic OR. This is the pipe, we can say pipe symbol for performing OR operation. And again S1 bar and S0 and I1. This is the second AND gate. Similarly, we have two more AND gates. We'll copy this. The third input is S1 S0 bar, which is I2. And the fourth input is S1 S0, which is I3. So this is our 4:1 multiplexer. There is an error. What is the error? S0 is not declared. Okay, we have defined S1 and S2, right? So I will change it to S0 and S1. Right? Now it is clear. So we'll give the order 0 first. 1 second. Okay. Now let's save this. And first thing we need to do, we have to check the schematic. Yes, this is the schematic of the 4:1 multiplexer that you have created. Notice that it is only using the 2 input gates, even though you have given 3 input and 4 input gates. This is a 4 input OR gate and this is a 3 input AND gate. Even though you have given 3 input and 4 input gates, it has converted into 2 input gates, because in Verilog the primitives are always 2 input gates. If there is a multiple bit inputs, then it will down convert it into a 2 input gates like this.